Hello everyone, 5.3 definite integrals. A little bit of review from 5.1, 5.2, and 5.7. The first integral is called an indefinite integral. Recall that indefinite integrals, after you find the antiderivative, you add c onto the end. But a definite integral, the second example, we don't do that, right? It's got limits from a to b. We're going to talk a little bit about that today. So in section 5.2, we saw the integral of a velocity graph gave us the total distance, or the area under the curve. So let's say you've got your old Volkswagen Beetle. Oh, this is a really poor drawing. Muffler, a little bit of smoke, and you're traveling to Grandma's house, following all traffic rules at 30 miles an hour. Grandma lives 3 hours away. So 30 miles an hour, it's your velocity, traveling for 3 hours. The area under the curve, we said, represents the total distance traveled, or the distance traveled, excuse me. So to find the area under the curve, in this case it's nice, it's a rectangle, so we take the base times the height, which is 3 times 30, and we see that Grandma lives 90 miles away. Okay, so the integral of a velocity curve gives us the distance traveled. Okay. Furthermore, we can approximate the integral of f of x using what's called Riemann sums. Now, a Riemann sum does not give an exact value for the area under the curve. It only gives you an approximation. We've got 4 types: LRAM, which is left Riemann, right Riemann, midpoint, and a trapezoid. On this example, I'm going to use the function x squared, which has inputs 1, 2, 3. All right, we want to do 3 subintervals. We're going to go equal length. So the output of x squared when x is 3 is 9, when x is 2 is 4, and when x is 1, 1 squared is 1. So a right Riemann sum can be constructed if we have an equal width on our subintervals. Let's go 3 subintervals, so it makes sense to start on the right side on a right Riemann sum. There's our first rectangle, our second rectangle, and then our third rectangle. So the Riemann sum, really all that it is the summation of those 3 rectangles, right? We've got 3 intervals, so we'll have 3 rectangles. That would be true on an LRAM, a MRAM, and a trap, depending on how many intervals you have. So the area under the curve, right, the integral of f of x dx, can be approximated using this. So I'm going to take the base and the height of each of the rectangles, multiply them together, and add them up. So let's start from the left side. The base is a width of 1, the height is 1. The second rectangle has a base again of 1, but now a height of 4. And the third rectangle has a base of 1 and a height of 9. When I add these up, we could say that the approximate area under the curve would be 1 plus 4 plus 9, which is 14. Of course, that's an approximation. And if you'll notice here, in this case, it's going to be an over approximation. Right? It's an overestimate, right? Because the area we're including here, which I'm coloring orange right now, is an overestimate of said thing. So we can say at this point it would be an overestimate of the area under the curve f of x from 0 to 3. Of course, we got to make it a definite integral, because now what we're doing is we are evaluating on a specific interval. All right, so suppose that f of x, or the height, is negative. Well, all that we'd do is we would accumulate negative areas then. So let's take a look at this graph here. F of x, I don't really know what the function is, but what I do know is I know a few of the inputs and outputs. So I'm going to take this input-output of 3, 0, and I'm going to place that right here. Okay, same thing for 2, 3. This won't be perfect, but I'm going to attempt it. 4, -2. Let's go here, -2, and 5, -5. Okay, here's 5, -5. I probably should have put the 4, -2 over here, just planning ahead. So scratch that. Okay, now I want a right Riemann sum with 4 rectangles. Okay, so I'm going to start on my right side. I'm going to create a rectangle going to the next input output. right? There's my first rectangle. Rectangle 2. This rectangle is going to be interesting. It doesn't have a height. Okay, so that one is kind of hard to get used to at first, but let's just highlight these and see what exactly we're going to be adding together. Okay, so this first rectangle here will have a positive area. The second interval doesn't have any height, so I'm not going to be adding anything there. And then I'm going to be looking at a couple of other negative areas. Okay, there's my third rectangle and my fourth rectangle. You could pause the video right now if you wanted to add those up and see if you get the same answer that I do. I'm going to take the integral of f of x from 0 to 5, and I'm going to say that that's base width of the yellow rectangle would be 2, height would be 3. The next one has a width of 1, but a height of 0. The next one has a width of 1 and a height of negative 2. And the last rectangle has a width of 1 and a height of negative 5. Now where am I getting these 1s here? Well, that's the distance right here from x equals 2 to x equals 3, right? And then I go 3 to 4 and so on. So the area under the curve I could approximate to be 6 plus 0 minus 2 minus 5. And again, this will be an estimate, but it looks to me like a decent estimate for the area from 0 to 5 of f of x dx using a right Riemann approximation method would be negative 1. All right, so when f of x, let's generalize this. When f of x is greater than 0, we accumulate or we add positive areas. Okay, and when f of x is less than 0, we're adding negative areas, or you could say we're subtracting areas. We're accumulating negative areas. Negative areas. I can spell, I think. My teacher learned me. So the summary is that the Riemann sum will give you a net area, a signed area, right? So as I accumulate, it gives me the net, not the total distance. Okay, so the net area is called displacement, area above minus area below. Total area is the total distance traveled, or basically considering any area positive and just adding them all up. So if I look at this curve here on example 2, I see I have a positive 10. I have, and it says I have a 30, but I'd consider that a negative 30, and then a positive 50. All right, so my net area, I would take 10, I would add negative 30. Again, this is net. I consider this still negative, and add 50. I believe that comes out to be a net area of 30. However, when I consider the total area, or what we'll call the total distance traveled, I negate this. I take the absolute value of that, and I add it together. So it looks like I get 90. Okay, so the displacement would be 30, and the distance traveled would be 90. All right, so let's move on to a very abstract version of both of these, and let's define the Riemann sum to a definite integral. So first of all, what I want to do is I want to draw a function, and that function doesn't really matter what it looks like, but I'm going to choose, oh my gosh, there's a spider on my paper. That's awesome. Protein. Okay, I'm going to draw a function, and it's going to get kind of messy here with the algebra, but what I'm going to do is, well, you just follow along. All right, so here's my function f of x. All right, let's say that's f of x. I guess if f is continuous from a to b, let's call this a, and let's go out here to b, right? So here's f of b, and here is f of a. Okay, I shouldn't have put that there. Let's make that a little more clear. Okay, we divide the interval a to b into n subintervals of equal length. So if I took an interval a to b, the length of the interval would be b minus a, right? And then I divide it by n, and we're going to call that delta x. Okay, so I'm gonna basically split this interval up, right, into n rectangles. Okay, I'm just gonna draw a few of them, but I'm gonna draw a rectangle here, and I'm gonna do a right Riemann sum. Okay, I'm gonna draw a second rectangle here, and a third, and that'll continue on until I get to my nth rectangle. Okay, so let's talk about this x value here. All right, each of these widths are delta x. So there's my first delta x, and then my second delta x, still same width, and then another delta x. That'd be my third delta x, and this would be my nth delta x. Okay, so this value here, this x value, would be a plus delta x. Then this x value would be a plus 2 delta x. And then this one would be a plus 3 delta x. You're starting to get the pattern, I'm sure. And then the last one, b, actually would be a plus n delta x. So what's the point? Like, this is just nerding out and it's great, but why? Why are we doing this? Well, let's set up, and it won't make a whole lot of sense right away, but let's set this up as a summation of areas. So let's consider this Riemann sum. What would we really be doing? Well, what we'd be doing is adding up a bunch of areas, okay? And I'm gonna leave this blank for just a moment, but I want you to see what's happening. So I'm taking base times height, all right? So really what I'm doing is delta x times some function output, right, our height. So let's take delta x times f of a plus delta x. So if I took f of a plus delta x, that would be the height of this first rectangle. And then base again times the next height, which would be f of a plus 2 delta x. And then delta x times f of a plus 3 delta x. And we would add all that up to our, oops, I forgot the delta x on the outside. I hope for you type A's that doesn't bother you. But I would add all those up. And really what I've done is I've done a summation. For those of you in honors pre-calc, you've seen this quite a bit. I don't know if the regular pre-calcers have, but this is really the summation of f of a plus k delta x times delta x. All right, now that's a sum up to the nth term or the nth rectangle. What we can do on each of these is notice that each of them has a delta x involved. So I'm going to pull a delta x out and leave the rest, right? So f of a plus delta x plus f of a plus 2 delta x plus, I'm going to skip the third one and just fit this all in, f of a plus n delta x. All right, that's a right Riemann sum. Okay, it's equal to the sum from k equals 1 to n of f of a plus k delta x, notice these variables match here, times delta x. This is just the sum of all the heights times each of the widths, provided those widths are all the same. So that means that the area under a curve from a to b of f of x can be approximated by using this. But how could we make it exact? How could we make this area more and more accurate? By doing what? Making each of the subintervals closer and closer and closer to 0, right? If each of these little areas, right here and right here and right here, they almost look like triangles. They're not, but they look like triangles. We could make each of those error spaces, if you will, smaller by taking the limit as n goes to infinity of the summation that we have. Okay, so what would what would happen to delta x as n goes to infinity? That would mean that the number of rectangles would increase without bound, which means that this finite space would be separated into intervals that are smaller than we can even imagine. Okay, so the important things, the two important things I want you to be prepared to use are finding delta x, finding a, and finding b. This right here, you'll see, is another way, another form of what we've just delivered here, okay? And why is it important? Well, because it's potentially on the AP exam. Okay, we'll do some examples here on the next page, 2 of them, and then we'll move to our next lesson in the next video. All right, so taking a look at this first example, or example 3, I want to know which of the following limits is equal to x squared, or the integral of x squared from 2 to 5. So first of all, you want to do this. You want to identify what is f of x. Well, f of x is x squared. What is a? What is b? What is delta x? Okay. So let's take a look. We know that we start and finish at a and b. So we start at a, which is 2. We end at b, which is 5. So delta x will be 5 minus 2 over n. Delta x will be 3 over n. Okay, so right away I'm going to look at my options and I'm going to eliminate a and I'm going to eliminate c because I see delta x hanging off the end as 1 over n. Okay, so I want to identify whether my answer is b or it's d. So let's do that. So the next thing we would do is we would recall that we're doing this. We're going from k equals 1 to n of f of a plus k delta x. Okay, k delta x times delta x. What was a? A was 2. Well, I see both a is 2 here and a is 2 here. Let's think about what k times delta x is. Well, delta x is 3 over n. And there, that will delineate, I don't even know if that's the right word, but that tells us right there that d is our answer. Now let's just finish it off just so that we know why d is the answer. Again, we know that the limit as n goes to infinity of the summation from k equals 1 to n of f of a plus k delta x. What is f? F is x squared. What is a? A is 2. What is k delta x? That's 3k over n. And delta x, again, is 3 over n. And that right there is d. All right, we're going to do example 4, and that'll be the end of the notes for today. So let's get at it. We're going to go the other direction now. Let's take an integral from 1 to 3. Actually, this is the same thing, but whatever. That's fine. We'll do this example. Go ahead and pause the video. Try it if you'd like to. And I'll go ahead and complete it as is. So f of x is 1 over 2x minus 7. A is 1. B is 3. And delta x will be 3 minus 1 over n, which is 2 over n. So I could write the integral from 1 to 3 of 1 over 2x minus 7 dx as the limit as n goes to infinity of the integral from k equals 1 to n of f. Well, f is this, 2 times x minus 7, all underneath 1, times delta x. Delta x we know is 2 over n. What is, well, we have to plug in a plus k delta x. I'm going to try to fit this in here. Actually, I won't. I'm just going to put this in here. A was 1 plus k delta x, which would be 2k over n. All right, this item right here should be plugged in there, and we'd have our summation notation of that integral as a right Riemann sum. All right, that is 5.3, definite integrals. Ask questions in class. Have a great day.